Um, but in the recording, I'm probably not going to go through and cut out all the bits where we talk about how I'm breaking up. So it's going to be kind of an annoying recording to watch. Okay. But anyway, I should be recording them anyway, so thanks for reminding me. Okay. So Kirchoff's laws. They're a way of reducing physical circuits into just some mathematical equations that can be solved. We have two laws, the junction law and the loop law. And the junction law is just the basic idea we've already... Hello. This is going to get very frustrating.
We can see you, sir.
Hey.
Oh, no.
Take another shot, boys.
Okay.
So maybe just screen share. Maybe the video is tanking your connection.
I didn't even know I could turn off this video. I suppose I can, yeah. I suppose I can just... All right. How are we doing there?
Yeah. Good.
Yes.
Much better.
Oh, really? Okay, that's good. All right. So, Kirchoff's laws. Kirchoff's laws are a way of reducing circuits down into some equations that can be solved. So our two laws are called the junction law and the loop law, and they're really both just familiar things that we've already dealt with, but just kind of written in a more mathematical way. The junction law is just that idea that current, when it gets to a branching point, it can split. So at any node in a circuit, and node just means any point that you want to choose, any node in a circuit, use a different color, current in equals current out. So in the example here, we would just have I1 plus I2 equals I3 plus I4 plus I5 in the one above. So we're basically just saying whatever current goes into a particular point, that's going to be exactly balanced by the amount of current coming out. So that has to be true, or else you're going to have current, like electrons building up at a particular point in your circuit, and that's not what happens. Okay? So at any node in the circuit, the current in is equal to the current out. The loop law is maybe slightly harder to get your head around, but not much harder. And that one says, for any closed loop, in a circuit,
You've cut out.
I might have just stopped talking.
Oh, okay.
I was just writing, I think. For any closed loop in a circuit, the total potential difference is 0. Okay, so what do we mean by that? The idea is, let's suppose you start at any point on a circuit. If you were to take the potential difference between that point and the point right next to it, then you get 0. Andy, did you have a question?
Why are there two batteries in this circuit?
Good question. Because you could conceivably put two batteries in a circuit. And I want to demonstrate that Kirchoff's laws work no matter what you do.
Oh, okay.
Okay, so yeah, you're right. We've only ever seen circuits up to now that have one battery, but Kirchoff's laws work even if you have multiple sources of power. Okay, so what we're going to observe is that these two points here.
Could you repeat that? I don't understand.
So all I'm saying is we can have two You could conceivably, physically, you could put two batteries in a circuit. If you can physically put two batteries in a circuit, then we want to know what happens when you do.
So wouldn't they be facing the wrong way?
Yes, they are facing the wrong way in this case. That's absolutely fine as well. I really I want to do the most general possible case. Okay?
Oh, okay. Is that on purpose?
Yes.
Does the loop law also work for circuits with one battery?
Yeah, absolutely. The loop law, this is a completely general rule for all electrical circuits. And same with the junction law. These are both completely general. Okay. So the basic idea of the loop law is if we take the voltage across 2 points that are right next to each other in a circuit, then the measurement we're going to get will always be 0. Okay? So then what we can do is we can imagine keeping one end of our voltmeter here at a single position on our circuit, and then moving the other end progressively around the circuit past each element. Right? And so as we go past this first one, we'll get a measurement of that first voltage. And then as we put our point here on the second one, we'll get a measurement across the first 2. Then we'll go here, we get 3, and then we get back to here, and we have to get 0 again. So what that means is as the current flows around this circuit, and we don't even know which direction it's running around, but as the current flows around this circuit, the amount of energy it's getting from batteries must be exactly balanced by the amount of energy it's losing in loads, in any parts of the circuit that use up energy. So, and we've already come across that idea, right? That's the idea that we've been using whenever we've been looking at circuits, right? That as you go around the circuit, the total amount you're getting from the batteries must be equal to the total amount you're losing to the resistors. Okay? So the total
You
amount...
did actually cut out that time.
So you just space jumped right there.
Okay. All I'm saying there is the total amount of energy that you get as you go around a circuit has to be exactly balanced. So the amount you get from batteries has to be lost in resistors or somewhere along the way. Okay? So let me just put some numbers on these. Let's say this is a 5-volt battery, and this is a 2-volt battery. Can't really see that too, but 2-volt battery. And let's say this is a 10 ohm resistor, and this is a 6 ohm resistor. Okay. If we were going to analyze this circuit, what we want to do is we pick a current direction. Now you can pick it correctly or you can pick it incorrectly. It actually won't matter, right? Because the negative signs will just pop out nicely. But let's pick it correctly here. So if I think about this, I've got a 5-volt battery pointing one way. I've got a 2-volt battery pointing the other way. Which one wins? The 5-volt battery. So we end up with a current going this way around. And what we're going to do is, whenever we run across a resistor, we've got a current going around this way. And what we're going to say is, whenever we run across a resistor, we're going to count that as a negative voltage, right? So we're going to go negative V4. Then we're going to run across another resistor, and we're going to go, okay, negative V3. Okay? Then we're going to say, we're going to run across this V2 here, but we're running the wrong direction.
Wait, what, sir?
What?
So you cut off after you said V3.
Okay. So, so annoying. I don't think the video is helping, and it's probably making it harder for you guys to tell when I'm not, when I'm pausing versus when I'm cutting out. So let me turn my video back on. This is incredibly frustrating. All right, remind me to just next time just to record something like this, and I'll get you to do. I'll just check in with you at the end of the time. Okay, so as we're moving through, the idea is we're moving around a loop around this circuit, and just every time we go across a resistor, we're going to count that as, if we imagine the current going across that resistor, we're going to imagine the current is losing energy, so we're going to count that as a negative voltage. Going across this one, negative voltage. Then we come to a battery here, but this battery is pointing in the wrong direction. It's against our current. So we're going to count that as a negative as well. And then we get round to V1, and V1 is going to count as a positive because we're running the correct way across this battery. Right, so that's a battery which is giving us energy, not a battery which is taking it away.
Sorry, can you repeat that about V1? Sorry, sir.
Good. So V1, the orientation of this battery is in the same direction as our current. So we're going to count that as a positive voltage. So that's boosting up our energy, not sucking away our energy. Right, so we're going to count that one as a positive. And then all of that comes to 0 because we're back where we started. So as an electron makes its way around this current, around this circuit, it's losing energy at all the resistors and power supplies that are in the wrong direction, and it's gaining energy at the power supply that's in the right direction. Kirsten just asked a really good question, which is how did I know?
We missed a lot of that.
Okay, I'll rephrase and then I'll say the question. So as we make our way around the circuit, we've got elements which are taking energy out and elements which are bringing energy in, and we're counting them as positives and negatives as we're going around with respect to the current direction. Now, Kirsten asked, how do we know that the current goes this way and not the other way? We could have actually done it the other way, it turns out. And if we'd done it the other way, amazingly, it all sort of comes out correctly anyway, in a bit of a weird mathematical trick. So we could actually assume the current went the other way and we would still get the same result here. So what we want to do with these then is we just want to turn them into their values. They're sort of the real values using what we've got above. So it's going to be V4 is I times 10 ohms. So I times 10 ohms. V3, and that's a negative. V3 is I
You
times...
just froze, sir. We just lost 10 seconds.
Yeah, I'm just working through what I'm writing on this line, so I've just got to write it and then we can talk about what it means. Let me write it all first. Okay, so the idea here is I times 10 ohms, that's V4, that's this one here. I times 6 ohms, that's V3. They're both negative because we're losing energy across them. Then we have negative 2 volts because we're going the wrong way across this battery. And then we have positive, 5, not 6, positive 5 volts because we're going the correct way across this battery. Okay, and we get that out to 0 here. And then we can solve for I. Okay, so I'm just going to solve for I now. So I get negative I outside of 16 ohms equals, and I'm going to move these to the other side. So negative 3 volts. So I end up getting I equals positive.
So why would the I be negative? Okay, yeah, got it right.
Just
now,
from
yes,
the line, just from the line
no,
above,
no,
yeah. Now, more fully answering your question from before, Kirsten, if we'd said the current were going the other way, if we'd said the current was going the other way around here, then what we would have got would be, then we would count this one as positive, this one as negative, these guys would still be negative, but what would have happened is the I actually would have come out as a negative number when we solved. And we'd go, if the I comes out as a negative number, I must have assumed the wrong direction. All right, let me show you how to use Kirchoff's laws in a relatively sort of a moderate to a moderate level circuit analysis question. So we're just going to do one sort of parallel circuit with maybe a slight complication. Let me show you how to use these two rules. Okay. So let's suppose we start with a circuit like this. 8 ohms there. So we got 30, so we got 20, 30, and 8 ohms there, and I'm going to put 24 volts on this. Okay, so we need to look for how do I bring up chat? Alt H.
Oh, he's gone.
Yeah, if you am I here?
We can hear you now. I don't know if you cut out when you stopped talking, but the last thing we heard was you need to look for or something like that.
Yeah, okay. I'm sorry. Okay, I'll tell you what you need to look for then. What you need to look for is junctions. So junctions like this here, we're going to have current going in and current going out. Okay, so I'm going to call that junction junction 1. Right, and then I'm going to look for another junction. Here we're going to have current going in and current going out. And let me call that junction number 2. And as far as I can tell, there are no other interesting junctions in this circuit. So I'm just going to leave those ones. All right, so these we're going to use Kirchoff's junction rule at those two. And at junction 1, what does it tell us? Well, we need to give names to these different currents. So I'm going to call this one here I1 going in, I2 coming out, and I3 coming out there. So I1 tells us, point 1 tells us that I1 equals I2 plus I3. Okay? Applying the junction rule at number 2. Inputs equals outputs. Well, hold on. That's I3. It passes through here, so that's I3 there. I2 goes around here, so that's I2 there. And then we could call this I4. Oh, but we actually noticed that I4 is actually the same as I1. So what we get there is I2 plus I3.
Sorry, what was that, sir? The last thing you said was we could call this I4.
Oh, we could call this thing I4. So we could do that there. Let's do that. But then we can see pretty quickly that either mathematically or using the picture, we can see that I4 is I1. But also mathematically, we can see that I2 plus I3 equals I1, I2 plus I3 equals I4. So I1 and I4 are actually the same number. Okay. Now we're going to use the loop law. The loop law is the more powerful one. Okay. So what we do is we draw any loop we like in our circuit. Okay. So let's draw one. I'm going to draw this one here. Okay. And you pick a direction. Now, as much as you can, try and pick the direction that you actually think the current will go in, but it's not always going to be possible. You're not always going to know. So don't worry too much about it. But I'm going to pick that direction there.
So the last thing you said was no, and then you cut out.
Pick a direction. So pick any direction for your loop to go in. Where you can, it's handy to pick the same direction that the current is going in, but sometimes you can't, and that's fine. And it won't stuff you up as long as you're careful.
Okay.
Okay? So let's go the green loop. That first loop there. And let's look at all the elements along that loop. So it's going to be positive 24 volts gets pumped into our loop. Then we're going to lose some voltage across this one here. And the amount of voltage we're going to lose is going to be 8 ohms times I1. V equals IR on that resistor. So it's going to be I1 times 8 ohms. Then we're going to go across the 20 ohm resistor, and it's going to be I3 times 20 ohms is going to be the amount lost on that one. So minus I3 times 20 ohms. And then we get back to where we started, which means, sorry, let me mark a starting point here. Let's call that my starting point. So we're back to where we started. So we say all of that equals 0. Okay? Now we're going to do a purple loop. Purple loop, we're going to start in the same spot. We're going to go around this way. And we're going to make our way around the loop this way. You don't have to call them by colors. You can call them 1, 2, 3. You can call them whatever you like. Right. So as we go around that loop, once again, we get 24 volts to begin with. We lose that same 8 ohms times I1. That's going to be V on that first resistor. But then this third term is different because we're going a different path now. We're going through this 30 ohm one. Okay, so that's going to be minus not I3, but I2 times 30 ohms. And all of that equals 0 because we get back home again to the purple dot. Okay, all right, so now we've got 4 equations and we've only got 3 unknowns. We've only got I1, I2, and I3. So we're actually going to be able to solve here, but there's actually one more loop in this diagram that I haven't done. So I'm actually going to write down that loop as well. And you can always sort of add more and more loops by looking harder and harder at your circuit. The last loop I want to add is this one here.
You're
Yeah.
cutting out, sir.
The last loop I want to
Cutting
add
out.
is, I'm so sorry. The last loop I want to add is this one here. And this loop here is strange because it doesn't have any power supplies on it. Okay, so I'm just going to assign a direction here. So I'm just going to say, okay, I'm going to go this way. Right, and we're just going to see what happens. Okay? All right. So I'm actually going to leave, oh no, I'll write it down. I'll write down that one for us as well. Okay, so here's where something gets a little bit complicated. So pay attention to this bit and make a special effort to interrupt me if I start cutting out here. Okay, let's say we start
You
here.
cut out, sir.
Okay,
So the last thing we heard was, fortunately, this is where it gets a bit complicated. And then we didn't hear the
the thing I said after that was just make a big effort to interrupt me if I do start cutting out here. So you've fulfilled the brief. Okay. So we're going to start here. We're going to go through this first one. And that's clearly, we had some current here. We're going down. We're losing some energy as we go across this. So that's going to count as a negative like it always has. So that's going to be I3 times 20 ohms. And that's going to have a negative on it. Okay. But then we keep going around this way. And now we're actually going, when we get to this resistor over here, we're actually going backwards across a resistor. We're going from the negative side of the resistor, the side closer to the negative terminal.
You're gone, sir.
I'm gone.
The last thing we heard was we're going backwards over a resistor.
Oh, okay, that's good. All right, we are going backwards across a resistor. We're starting off closer to the negative terminal, and we're going back towards the positive terminal. So because we're going from low voltage to high voltage, we're going backwards across the resistor, this one is going to count as a positive. Okay, so this one here is going to be I2 times 30 ohms equals 0. But we get a positive on this one because we're actually going backwards against the current on this resistor. Whereas on this one here, we were going with the current traditional style, losing energy across it.
Cool. We're with you. So
Okay, good. So what this allows us to do is it allows us to sort of take an equation, and by drawing more and more loops on it and looking at every single junction, each loop and each junction gives us an equation. And that lets us solve for I1, I2, I3, whichever I's you have in your problem, you can now solve them as simultaneous equations. Right? So what I'm going to do is, I don't know whether do we want to sit here and solve it together?
yeah.
Or can we see, or can we just see that this is something you can just plug into your CAS now? Well, let's do it. Let's do. I'm going to start with this one down here. I3. So if I rearrange this one, I2 times 30 ohms equals I3 times 20 ohms. Notice that that one is just saying these two guys get the same voltage. Right? That the V1 or V this one is equal to V this one. And that's the sort of rule that we expect for parallel components. So what the loop law does there is it just recovers that rule that we have that parallel things get the same voltage. Right? But that means I can then plug this one in here into these equations here to get rid of I3. And so these guys are just going to become equations of I1 and I2. Right, so let's do that. So these, both the green and the purple, become 24 volts minus I1 8 ohms minus I2 30 ohms equals 0. Right, so the purple one now, because by using this substitution down here, the purple one and the green one are now just equivalent. And so it's as if we've only got a single resistor problem. We can also use this guy up here, right? We can say I1 is going to be equal to I2 plus I3. So we can say, okay, 24 volts minus 8 ohms I2 plus I3 minus I2 30 ohms equals 0. And then we could also plug in I3 equals 1.5 I1 using that rule down there.
Sorry, sir. How did you get the 8 ohms out of the brackets?
No, there was no brackets going on here. I just replaced I1 with I2 plus I3 from up here.
You've gone so sorry.
Sorry, So what I've done is I've taken this relationship here from the junction and I've just replaced I1 with I2 and I3.
Okay, thank you.
Right? And then what I'm going to do is I'm going to take this equation down here, the orange equation, and I'm going to replace I3 with 1.5 times I2 because it's, So we're going to get 24 volts minus 8 ohms. This is I2 plus 1.5 I2. So that's 2.5 I2 minus I2 30 ohms. We're getting there. Just tight. We've only got one unknown here now, just I2. 2.5 times 8 is 20. So now we got negative 50 ohms I2. This is just maths at the moment. So if you're not following this, you can just reconstruct it later. But I2 is then going to be 24 volts divided by 50 ohms equals 0.48 amps. All right. I3 is just 1.5 times that. So that means I3 is equal to,
So where did you get that I2 plus I3 is equal to 2.5 I2?
oh, so,
Isn't it 1.5?
well, I3 is 1.5.
Oh, no. Oh, so would it be 3, sir?
Sorry, hold on. Let me go. I3 equals 1.5 I2.
Yeah.
And then we add on another I2. So I2 plus 1.5 I2 is 2.5 I2.
So could you repeat that you cut out?
Yeah, sure. So I3 is 1.5 times I2.
Yep, you cut out, sir.
I think the
I3,
idea is that I3 is 1.5 I2, and then you're adding on an extra I2. So 1.5 plus 1 is 2.5.
Okay.
Yeah.
Oh, okay.
so that let us solve those, and then we can go right back to rule number 1. So we're just going to add these two together to get I1. So I1 is going to be 1.2 amps. Then once we've got all the currents, you can then get any voltages you want just by multiplying those currents by the particular resistance they're going through. So if you want to know what's the voltage across this 8 ohm, well, you just go I1 times 8. So 1.2 times 8 is, shouldn't use that example, 10.4 volts on that one. And what you'll find is you can use any of these other loops, any of these other equations now to check what you've got, to start plugging in your values and check that they work. You will always generate more equations than you need through this process. So this process will never leave you short. It'll never leave you trying to find, 3 equations for 4 unknowns or anything like that. It'll always be, you'll always have extra, more than what you need. Okay, so if you are, now, that was not meant to take as long as it did. Sorry about all the cutting out. If you are very mathematically inclined, then this can be a very quick way to analyze quite difficult circuits without having to sort of go through like the metaphysics of like, oh, these two resistors count as this effective resistance, and that process of redrawing, which can get a little bit tedious. If you're just a kind of a mathsy person and you prefer to just do it in algebra, then Kirchoff's laws can be really useful. If you're more of a picturey person, then doing the redraws, either the mental redrawing or like the actual physically redrawing, can usually be maybe a more useful way to approach. But both of them do the same job. Both of them in the end get you all the currents and the voltages that you need.